As was said, the title here, Quantum Extremal Islands Made Easy. This was such a good title. In fact, we used it for 3 different papers, which are listed down here at the bottom. And I have to acknowledge that I had a number of co-authors working with me there on those projects. As with many of the talks we've seen, what I'm going to be talking about is new insights into the black hole information paradox. And so I'm going to have a quick review, although we've seen this review a number of times already. Basically, Hawking's observation was that we might think about a gravitational system where we start on an initial time slice here with a pure state. There might be excitations in that state that collapse to form a black hole. But then his observation, Hawking's observation, was that when we take into account the thermal fluctuations, that in fact the black hole leaks and that radiation appears carrying off energy at infinity here. Eventually, all of the radiation or all of the energy is carried off and appears in the radiation here. But further, his calculation indicated that this radiation was in a thermal state. And so that presented a basic tension with quantum theory, in that we've got an evolution where we started with a pure state and ended with a mixed state. And so there's a contradiction with unitary time evolution. Now, I'd like to phrase that problem or issue in terms of an entropy question, and we've seen that before as well. This is work that was originally done by Don Page. If we think about the entropy of the radiation here near infinity, initially there is no radiation, and so it's 0. But as the black hole creates more and more Hawking radiation, that entropy just continues to rise. And as I said, it continues to rise all the way to the end, or the evaporation of the black hole. And at that point, no more radiation is created. And so the entropy is just saturated and sits there. But that reflects the fact going from 0 to some final entropy reflects this going from a pure state to a mixed state. However, what Page argued was that in a situation where this is actually unitary time evolution, that entropy should be bounded by the entropy of the black hole. And so somewhere near the midpoint of the process, in fact, rather than rising, the entropy should start to decrease and eventually end at 0 when the black hole disappears again. And this would mean that there are extra correlations, hidden correlations, between the quanta that are emitted in the early part of the process and the quanta that are emitted in the final part of the process. And it's through those extra correlations between the degrees of freedom out here that we're going back to the pure state in this proposal where it is actually unitary. Now, the surprising thing about a year and a half ago is that there are now controlled calculations that compute the Page curve. And these were the first 2 papers that came out in the spring of 2019. And I'm also going to be referring to this 3rd paper that came out the following August. But then there have been any number of authors who have been contributing to this, and this is only a partial list. I could fill the whole page with people who have been contributing to these new insights, and I'm sure many of them are in the audience, and I apologize if your name doesn't appear here. In any event, I want to look at the summary or the conclusion that our friends here in Princeton came to, which was that there's a simple rule by which we can characterize the calculation, known as the island rule. And essentially, well, a key step is that we think of not just the black hole and the gravitating system, but we think of that as being coupled to an auxiliary reservoir where we collect all of the Hawking radiation. And that's typically a non-gravitational reservoir And so it's in some sense an external system that we're coupling to the gravitating system. But in this context, then we may ask, what is the entropy of the entanglement entropy of the radiation that we've collected in that reservoir? And the correct answer is given by this formula here. And as appeared, say, in Raphael's talk last night, this morning for you, there is a standard calculation that one can do for the entanglement entropy of these quantum field theory degrees of freedom. But in fact, we embellish that calculation because we include not just the entanglement of the degrees of freedom in the reservoir, but we also think about including degrees of freedom of regions in the gravitating system, and those are known as islands. But if we're going to include an island, we also include a gravitational contribution coming from the boundary of that island in the gravitating system. And so the idea here is that we test out all possible islands and find an extremum for this formula here. And then if there are multiple extremum, we choose the minimum value. And in this way, in fact, we essentially recover, or it's a procedure that leads us to a unitary curve for the entropy. And in particular, if we're thinking about an evaporating black hole at early stages in the evaporation, in fact, the island is the empty set, or there is no island. And so in this calculation, we're simply calculating the entanglement entropy of the degrees of freedom in the reservoir. And that's essentially what Hawking was doing. And so in this phase, the entropy starts at 0, but then starts to rise. But then at late stages in the process, when there's a large amount of entanglement between the degrees of freedom in the reservoir and the degrees of freedom behind the horizon, what we find is that there's a new saddle point, or there's a new extremum here. And there's a non-trivial island that appears. And in that phase, the entropy actually decreases and goes to 0 eventually at the end of the evaporation process. Now, there are a number of new, this is a new result, and there were a number of new ingredients that go into that. The first one being that we're coupling the system to a non-gravitating reservoir. And in the holographic context, what that meant is we had to change the boundary conditions on our ADS space to allow the Hawking quanta to leak out of the ADS and into this non-gravitating reservoir. And so there's a change in the boundary conditions. And then there are some other features. The early calculations focused on a certain two-dimensional theory of gravity, and it used this idea of quantum extremal surfaces. So I just very quickly want to mention that. We've seen JT, or Jaquet tidal volume gravity, a number of times. The essential point is that in 2 dimensions, the usual Einstein term is topological. And so in JT gravity, what we do is we introduce an extra scalar field, and the action takes this form here, where there's a scalar coupled to r minus the cosmological constant. And this effective action appears in various contexts, either from a dimensional reduction or in the so-called holographic dual of the SYK model. It's a simple theory, but a key in what we're going to be doing is we're not just going to consider the gravity alone, but we're going to couple it to a set of matter degrees of freedom that move around in this gravitating space. And for us, we're going to focus on conformal field theory degrees of freedom, or in the early calculations, that's also what appeared. Now, the simplicity of the gravity theory can be seen if we look at the equation of motion for the dilaton. It's just that the Ricci scalar is equal to a constant. It's just these 2 terms equal 0. And as a result, when I talk about black holes, people write down interesting metrics like this, where it's clear there's a horizon at this position, r equals mu. But in fact, this is simply an interesting coordinate system that's been put on two-dimensional ADS space. With that simple equation, in fact, the geometry is completely fixed, at least locally, to be a uniform negatively curved space-time, i.e. two-dimensional ADS. Of course, in this background, there's also a dilaton, and much of the interesting dynamics of this theory comes from the scalar field. But again, I'm emphasizing that when I talk about a black hole, I'm really just talking about a uniform geometry, and we're choosing coordinates more or less like Rindler coordinates so that there appears to be a horizon in that background. Now, we were going to be talking about entanglement entropy, and so the first thing in this holographic context we should do is ask, what is an interesting entanglement entropy question to ask? Our boundary theory, our gravity theory is two-dimensional, so our boundary theory is only one-dimensional, i.e. there's only time. And so we can't talk about entanglement between different spatial regions. But in this context, we can talk about the entanglement between the degrees of freedom on this side at this asymptotic boundary with the degrees of freedom on the opposite asymptotic boundary. And in this context, if we follow the usual Ryu-Takanagi prescription, the extremal surface, what we would be extremizing is the coefficient of the Ricci scalar, or the Einstein term, which is the dilaton over 4G. And the extremal surface would turn out to be the bifurcation surface here. And that's more or less what we expect. That's what we experience or we see when we look at black holes or eternal black holes in a holographic setting. Now, I said that the new ingredient was to think of quantum extremal surfaces. And there, what we're extremizing is not just this geometric factor, but we also take into account the entanglement entropy of the quantum matter fields that are moving around in the space-time. And so in this case, we don't just evaluate or consider the extremal surface, but we have a partial Cauchy surface that extends from there out to the asymptotic boundary and the region that we're interested in there. And in my picture, I've drawn two different Cauchy slices just to emphasize that because of unitarity, the contribution of the quantum entanglement entropy will be the same for both of those space-like slices. And so the way that we extremize has to be really coming from moving this surface around, not by choosing different Cauchy slices here. And this was really appeared in the early literature when people were considering 1/n or quantum corrections to holographic entanglement entropy. But you can see in the island formula here that we have both these geometric contributions and these quantum contributions. And so what this is, this extremization is an extension of the original holographic entanglement entropy formula. Now I want to make this discussion more concrete by thinking of an example, but the example that I'm going to give is not the evaporating black hole that I've been discussing so far, but a thermal equilibrium that was originally discussed in this paper by our friends in Princeton. So there again, I'm taking the same system, my JT gravity coupled to a CFT. And what I want to do is I want to prepare a black hole, an eternal black hole, and I want to put it in thermal equilibrium with a thermal bath. So the first step here in the gravitating system, we know that the way to prepare a thermal black hole is with a Euclidean path integral where we consider this instance on. So the geometry is now Euclidean. The Euclidean time is periodic, and the inverse or the period is the inverse temperature. The horizon in our Euclidean geometry just becomes a fixed point for the isometry associated with Euclidean time shifts here around this periodic circle. Now I want to couple that to a non-gravitating bath. And so in the non-gravitating system, again, I can prepare a thermal state with a Euclidean path integral on a periodic geometry. the fact that the periods or the circumferences here match in my picture is just a cartoon way of indicating that these two systems are being prepared in thermal equilibrium. Now, how do I actually get a state that I can manipulate? Well, I'm going to take this Euclidean path integral and I'm going to slice it in half along this dotted line. And then there's a quantum state that lives on that surface. So I might, redraw the picture. I'm squashing my Euclidean path integral out on the page here. And I've prepared the state on this dotted line. And I can now evolve forward in Lorentzian time. In the gravitating region, I produce my ADS2 black hole. In the bath regions on both sides here, I just get flat space. And I can think about evolving forward or backward in time. The key point is that we've prepared this very special state on a particular time slice in this geometry. Now you might ask, well, where is the information paradox? I mean, I've got a thermal equilibrium, nothing is changing, there shouldn't be a problem. But in fact, equilibrium means that there are quanta that are moving around in the space-time, and it's just that an equal number of quanta come out of the gravitating system as go into the gravitating system out of the bath. And so this continuous exchange actually leads to an increase in entropy. So here's an example. Our path integral may have prepared two correlated quanta here. This quanta heads off into the flat space and travels forever through the reservoir. This quanta falls into the gravitating system and eventually disappears behind the horizon. And so a process like that increases the entropy between the reservoir and the gravitating system. Similarly, quanta may go the other way. I've got two correlated quanta in the gravitating system. One escapes out into the bath, the other again falls into the black hole. So what should the page curve look like? Well, from this continuous exchange, naively, I said the entropy is increasing. That's a process that continues forever. And so you might think that you get a curve like this, where the entropy or the change in the entropy from our t=0 slice starts increasing, but then it continues to increase forever. But in fact, if I think that the black hole is a quantum mechanical system that can only store a finite amount of information, eventually, in some sense, we filled all the reservoirs, and further exchanges involve recycling quanta that have come in from the bath originally. And so in fact, what we expect or should expect in this case is that the entropy saturates at a certain point and just continues along as a constant. And I think we saw something like that in one of the earlier talks. And in fact, what our friends here in Princeton did is they thought about this particular system and this configuration. They applied the island rule, and they found that certainly in the early stages, there was this growth phase where in fact there was no island, there was no extra contribution coming from the gravitating region. And then eventually it went over to a new saddle where the entropy was saturated. And in that phase, there was a contribution coming from a region in the gravitating system, and that involved the quanta near the black hole horizon or behind the black hole horizon. I'll also add that a surprise at the time was that the boundaries of that island, or the quantum extremal surfaces, actually appeared outside of the black hole horizon. You might remember from Raphael's discussion this morning that when he talked about the quantum extremal surface, he seemed to indicate that it was behind the horizon, and in the evaporating case, or in many cases, it is, but it was a surprise then that here, quantum extremal island extended outside of the horizon. And so that's, these early calculations gave us a remarkable new set of calculations. They also raised many questions about, was the focus on 2 dimensions important? Was the JT gravity important? And what the main message of my talk today is that, in fact, we can extend these calculations to higher dimensions fairly easily. And in fact, we can understand the results using more familiar properties of holographic entanglement entropy. And so that's not to take away from the new insights, but it's to frame it in a context where we have more familiarity with it, with the situation, and so perhaps to gain even further insights into the unitary page curve. So actually, I'm going to stop there and ask if there are any questions. That went by, it was mostly review, but it went by very quickly. So I'll just pause and ask if there are any questions about that. I'm not seeing any, so I'm just going to continue ahead. So to get to this new model, I'm going to step back 20 years and go and think about something known as Randall-Sundrum gravity. And what those folks did is they did something, well, they found something remarkable. And that was that if I take an ordinary brane, a codimension 1 brane, and stick it in an anti-de Sitter space, the back reaction actually creates a new graviton mode that's localized in the vicinity of the brane, and it leads to an effective theory of gravity on the brane. So the idea here is that I'm just starting with ordinary Einstein gravity, negative cosmological constant in the bulk, and I'm coupling that to a brane with a finite tension, so it's going to back react on the system. I'll add as an aside that, to really make a parallel with the JT gravity case, we could also consider adding intrinsic gravity terms on the brane, but I'll just say that you can go to the papers for the details there. That's not important for anything I say today. But the result is that if we integrate out and we think of the physics on the brane, what we find is an effective theory of gravity. So there's an effective Newton's constant here that depends on the bulk parameters. There's a cosmological constant here. You can start to see the interaction or the back reaction. Here's the tension coupled to gravity in the bulk. And then there's an Einstein term. And then in fact, there's a whole series of higher curvature terms that appear as well. Now, we're going to tune things such that the cosmological constant is small. And what I mean then is that the effective curvature scale on the brane is much larger than the ADS scale in the bulk, or alternatively, that the brane cosmological constant is much smaller than the bulk cosmological constant. And what that means, as far as the effective theory is concerned, is that the contributions of all of these higher curvature terms is actually going to be suppressed by the ratio of these two scales. And so effectively, what we're working with is a theory of Einstein gravity in d dimensions. Now, what does the geometry look like, or how does the brane really fit into my ADS space? Well, we can understand that using the Israel junction conditions. Here's a cross section of my d+1 dimensional ADS. I'm going to foliate that by slices that themselves are ADS but one lower dimension. I'm going to cut off the geometry at some value of rho on one of these slices. And then I'm going to make another copy of the geometry, glue them together. And the Israel junction conditions then tell me that the jump in the extrinsic curvature is related to the tension of the brane. An interesting thing is that you can also determine that position by using this effective action and simply solving the equations of motion. And what that will do is it'll say that the curvature of the brane is related to this cosmological constant. There are contributions of higher curvature terms if you work more carefully. But in any event, what this scale does is it fixes the position of the brane in this foliation of ADS space. And so the fact that you can use either approach is just an indication of the consistency of this description of the brane in terms of Randall-Sundrum gravity. A warning is that, this is already a cartoon. It's a more appropriate cartoon that characterizes the geometry, but I'm going to be lazy and I'm going to be drawing pictures like this. And you should just remember, when I draw a picture like this, the green line means there's a brain in the middle of my ADS space, but there's lots of extra geometry actually implicitly hidden in this region here. And I'm just, again, I'm being lazy not to draw a more accurate depiction of the system that I'm looking at. In any event, what we have is then actually three, instead of just two, we have three different descriptions of our system. We've got this bulk description of a brain in ADS space that I was just talking about. Holography tells me that there's a boundary description in terms of a boundary CFT. That boundary CFT is coupled to a defect where the brain extends out to infinity, and there are conformal degrees of freedom on that defect as well. But then there's this sort of midway story where what we do is we do holography for the defect degrees of freedom, and we describe it in terms of gravity on this ADS space in D dimensions here. And I should say that on that surface, again, according to the usual Randall-Sundrum prescription, we get a copy of the boundary CFT. However, it's a boundary CFT with a cutoff. And in fact, in the construction that I'm giving you, there are actually two copies because there are two sides of the brain. And so each of the sides of the brain, in a sense, induces one of the copy of these CFTs. But it's really this, we've got the usual boundary perspective, the bulk perspective, but there's this picture, which I'll call the brain perspective, which is really now a system of gravity in an ADS space coupled to a CFT in a non-gravitating region, namely the asymptotic boundary. And so this is going to be the picture where we can really discuss things like islands and or compare to the previous models or scenarios that I was talking about. So I wanted to have a black hole. And so for the moment, what I'm going to do is I'm going to set the brain aside. I'm just going to think about ordinary empty ADS space here. And I'm going to remind you that, in fact, I can find a set of coordinates where that empty ADS is described as a hyperbolic black hole. And so here's a metric on ADS space in D+1 dimensions. However, you can see that it's a coordinate system where there's a horizon. And so that's depicted as these orange disks in my ADS space. And so sometimes this is called ADS Rindler coordinates. What's the description in terms of the boundary theory? Well, what we're describing here is a thermofield double state, as usual. That's what we get when we have an eternal black hole. But the geometry that the CFT lives on is now, well, there's time, and that's the R direction. But the boundary geometry, the spatial geometry, is actually a hyperbolic plane in D-1 dimensions. There's also a there's a tuned temperature here. The temperature is related to the curvature scale of this hyperbolic space. And so there's the formula. The temperature is 1/2 pi r. And I've just, in this picture here, shown the two boundary regions that are entangled in the thermofield double state. And this picture on the side here is just to show you that what one finds is that a Penrose diagram for this geometry that looks essentially like the Penrose diagram of empty Minkowski space. Now, I wanted to introduce these brains, and so all I'm going to do is I'm going to take a brain and stick it in the middle of that space in that coordinate system. And now what I get is, again, that thermofield double state, but the CFT is now coupled to a conformal defect, namely this region here where the brain extends out to infinity. However, the geometry aside from that is identical and the temperature is identical. And I might also add that the geometry on the brain or the natural induced metric on the brain has this hyperbolic black hole geometry, and that's just inherited from this coordinate system in the bulk. So I just want to emphasize that I've now set up a system in higher dimensions that's very much like this system that I talked about when we were talking about the two-dimensional model. There we had our ADS space with Rindler like coordinates, and we had two flat space geometries coupled to either side. Now what I have, when I think about it from the brane perspective, is I've got an ADS space on the brane in D dimensions. I've chosen coordinates so that there's an ADS or a Rindler-like horizon. That's coupled to the asymptotic CFT in these non-gravitating regions. Instead of flat space, I have time across a hyperbolic plane. And another difference is that instead of the gravitating system being coupled to the end of the geometry, it's now coupled in the middle of the asymptotic, well, this bath geometry. But again, I've got a gravitating region with a black hole coupled to two non-gravitating regions on either side. Let's think about entanglement entropy now. So this is my boundary geometry. In fact, I've got two copies of that. What I want to do is I want to ask about the entanglement entropy of the bath degrees of freedom, or the degrees of freedom in the reservoir. And so what we do is we pick a region that is a small step away from the defect and then extends out to infinity on either side in the bath. One of the interesting points is that if you evolve in time, the natural time flow for this region, well, the time flow in that geometry, in that Penrose diagram, looks like it's in the same as in flat space. And so these points move up towards the peak here, time like infinity, i.e. they're converging on this point at the top of the diamond. Another interesting point is that if I think about the infinities here, you can see in this diagram that the infinities actually touch. And so although I have sort of four regions, when I think about the boundary of the ADS space, in fact, there are just two regions because the infinities sort of connect up here. And so I really have a region extending, well, it's a small step away from the defect on one side and extends over to a small step away from the defect on the other side. And then we have the other side of the geometry on the other side of the defect. If we look at the time evolution in that picture where I've got a slice of my ADS, what we see is that the boundary regions, or these ends of the intervals for which we're calculating the entanglement entropy, are moving towards the brane, i.e. towards the tip up here. Now that may seem reminiscent because that's a situation that we may have studied entanglement entropy for before. In particular, something that we've seen when we looked at regions where there are two. So now I'm just looking at empty ADS space, but I've got two boundary regions, the two blue regions. One of the things we've known to expect is that there are two competing saddles that might give the minimal RT surface. In the so-called disconnected phases, when the blue regions are relatively small, the RT region just is a cap on either side. Whereas in the connected regions, the RT region reaches from one boundary over to the other region on the other side of the ADS space. Now, the interesting thing, I've shaded in the interiors of these RT surfaces to indicate the entanglement wedge. And I'll remind you that one of the things that holography has taught us is that the boundary degrees of freedom can tell us about the degrees of freedom in the bulk at the interior of the entanglement wedge. But that means when I go to the connected phase, I know not, or the boundary tells me not just about what's going on in the bulk near those surfaces, but it actually tells me in principle what's going on deep in the interior in the center of the ADS space. So I'm just going to take that familiar situation, and basically what I'm going to do is I'm going to draw a green line down the middle of it. And so now what I'm saying is I can take that experience and see how that applies now in our geometry where we've got this defect brane in the middle of the space. And in fact, what we find is the disconnected phase dominates at early stages. In this case, the RT surfaces are stretching across the horizon, which is this dotted line. Well, it's a cartoon, but it's a dotted line in the middle of the space like this. And as time evolves, the entanglement entropy grows. And of course, the entanglement wedge tells us about these two regions here. And this is the growth phase that I showed you on this page curve for the equilibrium situation. However, at later stages, what happens is the connected phase takes over. And so now the RT surfaces stay on either side of the horizon. They don't cross the horizon. And it turns out that the entanglement entropy is fixed in time. And further, by entanglement wedge reconstruction, we know in principle the degrees of freedom in these two blue regions can tell us what's going on in the middle of the space, i.e. what's going on the brane here in the interior. And really what that's saying is that the degrees of, first of all, what the new RT surface has done is it's defined a quantum extremal island in the gravitating system on the brane, but it's also saying that the degrees of freedom in the reservoir here can tell us what's going on in this region, in this quantum extremal island region on the brane. And of course, this is the Page phase. Now, it seems like I've done a real bait and switch here. I was just talking about ordinary holographic entanglement entropy, but then suddenly I was saying it indicated there were quantum extremal islands and whatnot. And I just want to, that's something that's really remarkable in this holographic setup, that all I'm ever doing is calculating these geometric entropies. You can ignore this term. This would be there if we had this intrinsic term on the brane, which we don't. So all I'm doing is calculating the usual Bekenstein-Hawking term in the bulk, but I'm giving it an interpretation in terms of the island rule here. And so how did that happen? Well, this is the bulk perspective, and this is the brane perspective. And see, so let's take a closer look. If I want to extremize the RT surfaces in the bulk, I'm going to do that actually in two steps. At a very pragmatic level, when we do our calculations, the first thing we do is we look at surfaces that are extremal in the bulk away from the brane. Namely, they satisfy some local equation having to do with the extrinsic curvature. And that defines a whole set of surfaces, in fact, in the bulk. And I want to emphasize that it's not a single surface that this equation defines, but a whole family of surfaces. And one way to understand that is that I've defined, I'm taking only half of the picture, and I've defined some boundary data here. Remember, I introduced a cutoff here. If I had the whole geometry to define a particular RT surface, what I'd have to do is I'd have to give you boundary data on the other side, on a putative boundary over here. But I'm not doing that. I'm just introducing this brane, and so I'm not specifying where the surface should end on this side. And so in fact, there's a whole family of surfaces or a plethora of surfaces that are defined by this step here, where I'm just extremizing in the bulk. We can look at the contributions of those family of surfaces. And one of the things we'll find is a set of geometric terms associated with UV divergences, where the surfaces approach the asymptotic boundary. I've got the word identical because those divergences just depend on the geometry of the entangling region here, and it doesn't matter what happens over here. And so in fact, all of those UV contributions are identical for all of these surfaces. Now, interestingly, there are some potentially divergent surfaces on the other side, except that we introduced this cutoff, the brane on this side. And so they're large contributions. They have this geometric form, But using the cutoff and our translation to the effective theory of gravity on the brain, this is the geometric entropy or the gravitational entropy coming from the brain. And in fact, that's the wall, if we work hard enough, we see the Wall-Dong entropy. So there's a Bekenstein-Hawking term here, the area over 4G, but then there are terms that are related to the higher curvature expressions that I hinted at before in the gravitational action. And of course, then there's the infrared contributions, the finite contributions coming from this stuff that's happening in the bulk. I can combine those two contributions on the left over here, and I can interpret those as the quantum field theory contributions coming from the boundary CFT, both in the asymptotic region and on the brain. And then these contributions are the gravitational contributions coming from the intersection of the RT surface with the brain over here. And so what this step of the calculation has done is it's turned our calculation into an evaluation of this expression that appears in the island formula. Of course, we haven't extremized our RT surface yet. What we have to do to find the truly extremal surface is we have to vary over these intersections, i.e. what we're doing is we're varying over or extremizing over the possible islands on the brain. And so that's sort of giving you the translation from bulk Bekenstein-Hawking entropy to a three-step formula that gives you first, this expression in the island formula. Extremizing, we saw in the second step that we're extremizing over all possible islands. And this minimization is like choosing between, well, am I in the connected phase or the disconnected phase? There are different possible saddles in our holographic entanglement entropy up here, and that's what this minimization is here, in the same way that it appears here. The one embellishment of this formula is that we had a higher curvature theory of gravity, and in fact, it's not just the Bekenstein-Hawking contribution, but in fact the full what I'll call the Wall-Dong entropy that appears here. So that's sort of an insight into what I've been, or some of the words that I'm associating with this simple interpretation of the holographic entanglement entropy. An interesting thing that you can do is consider, instead of the blue regions in this picture, consider the black regions. In that case, what you're doing is you're considering the entanglement entropy between two boundary regions that include the defects, but are on either side of the black hole horizon. This is something that Hartmann and Maldacena did a long time ago. And in fact, they found entropy curves very much like what we had before. The same bulk surfaces would be in play, but there the interpretation had nothing to do with page curves or anything like that. Their interpretation was that the system rapidly thermalized, and then the entropy was saturated, in fact, by an entropy inequality as it had to. Another feature from that perspective is that these surfaces are always some distance away from the horizon down here, and that is a result of something known as entanglement wedge nesting, but it also explains then why the islands in my higher dimensional or my equilibrium situation actually sit outside of the horizon rather than inside the horizon. Well, I'm coming close to the end, but I'm not showing you any of the details of the calculation, which are actually numerical, but using our higher dimensional system, we can generate page curves like the one that I described before for 2 dimensions, and you'll see a detailed explanation of this picture here or how we get those results in the papers. There were lots of questions, having to do with 2 dimensions, JT gravity, the ensemble average of SYK, and my example shows or suggests that none of those was important. We have a higher dimensional now example where we can do explicit calculations using Einstein gravity. And it's certainly not a theory that involved, or the standard rules that we're using do not involve any kind of ensemble averaging. A more interesting question was something that came up in Raphael's talk. Here I've got a formula, and I'm talking about entanglement entropies. Implicitly, here are two entanglement entropies, and they both involve the reservoir. But the two formulas get distinguished. Here, what we say, I said this was the correct entanglement entropy. What the authors or our friends in Princeton said or described it as is that this is the entanglement entropy in the full quantum description of the degrees of freedom. This is the entanglement entropy or this calculation involves a semi-classical description of the degrees of freedom. And so I just wanted to give, some hint as to, what is our picture saying about that? Well, it's really saying that I said that there were three effective descriptions or three descriptions of the physics, but they're really they're not on an equal footing. In particular, these two, that's the usual duality of the ADS CFT correspondence. That involves, standard holography, and that's what I'll call the UV complete description. That is, that is really the framework, or in particular, the bulk description. That's really the framework in which I was doing my calculations, but I was interpreting them in terms of this brane perspective. And we know that this is really only an effective description of the theory. I mentioned it very quickly in passing, but the Randall-Sundram prescription, or what they told us from the very start, is that this is an effective description of the brane physics. In particular, when I think of the CFT on the brane, I should think that it comes with a cutoff. And so it really stands on a different footing from the other two descriptions. And it's in this context that we see that we have an effective theory rather than a full theory of the gravity. And so that corresponds to the semi-classical description of the radiation and the Hawking partners. One of the things that this really emphasizes is that the island rule is really a mnemonic for the effective gravitational theory. This is a calculation that we can do relatively easily that tells us that the page curve should be unitary. But the framework of this effective theory here is not going to reveal these hidden correlations between certain degrees of freedom or the reconstruction of the interior of the black hole from the reservoir degrees of freedom. And so it's really a rule, as was emphasized in Raphael's talk. We're going to assume that we would apply it. In my context, what I had was a control of that UV description. And so I know that this was the appropriate way to do the calculation. But in general, well, if we compare to this, the paper by these authors, in general, we really have to know something about the UV theory to understand that this is the correct way to calculate the page curve. And I've run out of time, but I'll just say that, this is, again, a simple or relatively simple holographic calculation that puts many of these new insights into a more familiar framework. And so hopefully that'll allow us to make further progress in understanding the page curve. But of course, there are many questions that are still open. And so there's still lots to explore. And we've been hearing about some of that exploration, and we will continue to hear about it more at the conference this week. So at that point, I'll just stop and thank you for your attention.
Thank you very much. Nice talk.
Okay.
So question or comment? If you have, yes, Ugajin-san, please.
Thanks for the nice talk. So I'm just wondering, given the simplicity of this calculation, is it possible to generalize it to the calculation of linear entropies?
In principle, it is, and I was thinking, I've been thinking about that recently, but you know, in principle, all I'm using is the standard rules of holographic entanglement entropy. And oops, sorry. And so these surfaces are derived, or in principle can be derived using the Lukowitz Maldacena prescription, which is really a calculation of Rayleigh entropies. This is an art, if you like, a residue of a gravitating brane that sort of represents the twist operator in the boundary theory when the Rayleigh parameter is finite. The truth is we haven't, for the scenario that I've described here, I haven't pushed it further to, really identify or to show, how those, how the Rayleigh entropies are calculated. But I think it's a very interesting question. I'd be happy to talk to you about it later, if you like.
I see. Yeah, thank you.
Okay.
Next, Takayami-san, please.
Thank you very much for very interesting talk. I have two questions. First question, you in the middle you talked about the Lindora ADS and putting your brain. And my question is it possible to generalize that to the case with some orbitals like BTZ, like black hole, and so that it has some singularity in your scenario? And another question, yeah.
Oh, sure. Go ahead. No, go
another
ahead.
question is, could you also, in the final slide, you mentioned complexity. So I'm very curious about what we can see for from complexity for this island story.
Yeah. So in principle, yeah, you would like to study this not just in the sort of ADS Rindler context, but in the context of finite temperature black holes. I mean, your suggestion is an interesting one in that you're suggesting ADS3 or a BTZ black hole, which locally has a very simple geometry, and that may actually be a place where you can make further progress. In fact, I have a student who's working now on perturbing the temperature away from this finely tuned, this special temperature. And in that case, the geometry isn't quite ADS in these regions outside the horizon, but it's very close to ADS. Of course, deep inside the black hole, there'll be a singularity now, and so everything will become more complicated. But what we're working towards is a perturbative calculation, because most of the calculation, the calculations really don't rely on the details of what's happening deep inside the black hole, and it's more physics that's happening near the horizon or near the bifurcation surface. The other question, are you happy with that answer, or can I move on to the complexity? Is that okay?
Yeah. So
okay.
Yeah, I mean, so do you see anything special in the presence of singularity or this kind of?
It's a very much a work in progress, and so the singularity hasn't. Yeah, no, we haven't. In the calculations we've done so far, the singularity hasn't been that important for what we've done. There was also here. Let me just a second. There was a calculation. Well, there was a question about the holographic complexity.
Yes.
I'll just. me see if what happens when I do this. Nothing. Okay, I'm gonna have to flip through a whole bunch of stuff. Yeah. Originally, I mean, this nice story that I told you about the interpreting the holographic entanglement entropy was a warm-up for us for considering holographic complexity. And there you might ask, did I go to the right place? Yeah, there you might ask what happens with complexity. In particular, what we studied or thought about was complexity equals volume. And so there you would have a similar simple bulk formula, but you might ask, well, what are you going to get when you interpret it from the brain perspective? There's a very simple analysis that you go through that's very similar to the discussion of holographic entanglement entropy, and there are surfaces, there are variations over the intersection with the brain, there are the interpretation of the various contributions. But what you find is that actually there is a geometric contribution here. It's a contribution just like for the holographic entanglement entropy. It has contributions coming or that can be related to higher curvature terms in the effective theory of gravity. And then there's a contribution that you can understand as a quantum field theory contribution to the complexity. And so there's, well, one insight that you get is that if we step away from the brains and the page curve and all of that, there seems to be a natural generalization of complexity equals volume for higher curvature theories of gravity. And it seems to indicate that there is a quantum field theory contribution. But again, this is one of these things where you take one step forward and you're drawn by questions in a number of different directions. So there's really, well, that was very, very quick. I don't know if you want more details, but there are a number of interesting questions that you can ask having to do with complexity as well, holographic complexity. I mean.
Thank you very much.
Okay. Next, Tanahashi-san, please.
Maybe I have misunderstood, but at the middle of presentation, did you mention that the induced gravity term on the brain is relevant to JT gravity?
Oh, yes, I did.
Explain about, could you explain about it a bit more?
Yeah. Oh, well, it's, sorry. Yeah, here we are. It's really, if I start with this framework and I do the calculation in, well, 3 bulk dimensions, you won't you won't end up with a nice theory like this. I mean, you can see there's a d-2, and the bulk dimension was 3, so this is 0. And so the calculation works out a little bit differently. In particular, there's no degree of freedom in the theory that matches the dilaton. And so one way to interpret the result is that I should actually think that I have not just an ordinary brain, but that I've actually added essentially the JT gravity to my 2-dimensional brain. And so that then essentially lifts to the effective to the effective theory that you find for the brain gravity. And it was sort of motivated by that. I mean, we saw that this wasn't working the way that, or it wasn't working the simple way that Randall-Sundrum, well, that you might have hoped that Randall-Sundrum would provide. And so actually in the papers, there's a detailed discussion of how d = 2 is different. But seeing that you had to add in that context an extra term on the brain, it kind of motivated us to think, well, when I go to higher dimensions, I can do something similar. And this changes, it doesn't change the physics in an essential way. It changes, for example, the effective gravitational constant has a contribution coming from the brain now, as well as the bulk. There's some details about cutoffs and how the cutoffs appear. Remember, I said that this is an effective theory with a cutoff, and so there are details about where the cutoff appears in the theory and things like that. And it just enriches the systems and it doesn't really change the story, but it gives you an extra dial that may be useful in future studies where it may lend itself to pushing the system to different regimes that maybe have some special interpretation.
Let me ask another thing. And
Okay.
JT gravity can follow from, if I remember correctly, the near horizon geometry for higher dimensional spherically symmetric extremal horizon.
Yeah.
And from that picture, can we understand the origin of that induced gravity term? Which part of the near horizon geometry in higher dimension correspond to the induced gravity term?
Okay.
Is it a well-defined question?
No, I'm sure it's a well-defined question. I'm just trying to fit it into the way that I've been thinking. I mean, the dilettante is effectively the area of the horizon in the higher dimensional theory. I should be able to do this more quickly. I'm not thinking on my feet very quickly this morning. It may be that if you had an extremal horizon in ADS space, and then you stuck a brain through that region, that there would be a part of the theory that effectively near the horizon would be JT gravity. But I have to confess, I'm just stringing the words together. I'm not quite seeing it in my mind when I think about it. But it might be an interesting question to try and understand how to get JT gravity to come out of a construction like that. I mean, I might add as well a related. Well, it goes back to Tadashi's suggestion of thinking about ADS3. I think it's Eric Verlinde and a student. They were showing that a dimensional reduction of ADS3 was actually giving them JT gravity. And so that might be another context where it is another context where JT gravity appears. It might be something that by combining ideas of Randall-Sundrum gravity and ADS3, that would be a natural, that you wouldn't have to add an extra contribution for the brain. I hadn't really thought about that in any detail.
All right, thank you very much.
It's a good question. Yeah.
Okay, Ugajin-san, please.
No. Yeah.
No.
Right. Yeah. Okay. So just I mean that. Okay. So we talked about the difficulty of this obtaining JT gravity on the brain, but I thought that precisely as you said, I mean that the JT gravity is coming from dimensional reduction of the 3D gravity. So yeah. So somehow dimensionally reducing. Probably you can easily obtain this JT gravity on the brain. But I just wanted to comment that.
Yeah.
Thank you. Other comment? Other question or comment? If not, let's thank Robert again. And yeah, so now I'd like to close this session. The tomorrow session will start from 10:15. So yeah, see you tomorrow. Thank you for participation. So, thank you for Robert. Thanks. Yeah, very nice
Okay.
talk. Yeah.
Thank you very much.
Thank you very
Okay.
much for great talk. Oh,
Have a good evening. Yeah.
Yeah.
Bye-bye.
これは、ホストをちょっと一回戻した
はい。
方がいいですか。ちょっと違うな。これがいいですか。どこのこれか。
まだですね。